You think gravity pulls you down. You think you understand falling. You don't. Right now, as you're sitting there, you think the Earth is pulling on you with some invisible force, yanking you toward the center of the planet. That's what Newton taught us. That's what feels obvious. That's completely wrong. Gravity doesn't pull you down. Einstein proved it 100 years ago. But here's the thing that's going to break your brain. You're not falling toward the Earth. The ground is accelerating up toward you and down. Down is a direction your brain invented. Let me ask you something. When you drop a pencil, what happens? You say gravity pulls it down. That's not an answer. That's a label. You've just renamed the mystery. You're saying the pencil falls because of the thing that makes pencils fall. You haven't explained anything. You've just given the phenomenon a name and convinced yourself you understand it. This is where most explanations cheat. They dress up ignorance in fancy words. Gravitational force, attractive force, force of gravity. What's a force? How does the Earth reach across empty space and grab that pencil? What's the mechanism? Newton knew this was a problem. He said, I frame no hypothesis. He could describe how objects moved under gravity, predict where they go, calculate their paths with incredible precision. But he freely admitted he had no idea what gravity actually was. He just knew it worked. For 200 years, that was enough. Build bridges, fire cannons, navigate ships. Newton's equations worked beautifully. But they didn't explain anything. They were just very precise descriptions of how things fell. Here's where your intuition fights back. You feel weight right now. You feel the Earth pulling on you. How can I possibly say that's wrong? Because what you feel isn't what's happening. What you feel is your brain's interpretation of electromagnetic forces. The atoms in your body pushing against the atoms in your chair. That sensation you call weight, that's not gravity. That's the electromagnetic force preventing you from falling freely. Let me show you what I mean. Stand up. I'm serious. Stand up right now and jump. Not a big jump, just a little hop. Now, what did you just experience? You probably think you overcame gravity for a moment. Then gravity pulled you back down. But that's not what Einstein says happened. According to Einstein, during that brief moment in the air, you were in your natural state. You were free. When you were falling, you weren't being acted upon by any force. You were following the straightest possible path through curved space. It's only when you hit the ground that forces entered the picture. Let me tell you about the most important thought experiment in the history of physics. Einstein called it his happiest thought. Picture this. You're in a windowless elevator. Suddenly, you feel yourself pressed against the floor. Your coffee cup falls off the table and smashes. Question, are you accelerating upward, or is there a gravitational field pulling everything downward? The answer is, you can't tell. There's no experiment you can do inside that elevator to distinguish between acceleration and gravity. They're identical. Now here's the flip side. You're in the same elevator, but now you're floating. Your coffee cup hangs in the air. Your pen drifts slowly across the room. Are you in deep space, far from any massive object, or are you in free fall toward the Earth? Again, you can't tell. This is the equivalence principle. Acceleration and gravity are the same phenomenon, viewed from different perspectives. Let me push this further. Take out your phone right now. Feel its weight in your hand. That weight you're feeling, that's not the Earth pulling on your phone. That's the electromagnetic forces in your hand, preventing your phone from following its natural path through curved space-time. The phone wants to fall freely. You're stopping it. Now imagine you're in a transparent glass elevator, falling toward the Earth. You let go of your phone. What happens? It floats next to you. It's not defying gravity. It's obeying gravity perfectly. You and the phone are both following the same geometric path through curved space-time. But here's where it gets weird. To someone standing on the ground watching you fall, you and your phone are accelerating downward at 9.8 meters per second squared. From their perspective, you're speeding up, falling faster and faster. But from your perspective, inside the elevator, you feel nothing. No acceleration, no force. You're weightless. Who's right? You're both right. That's what Einstein realized. There's no absolute perspective. Motion is relative. Acceleration is relative. Even gravity is relative. But if acceleration and gravity are the same thing, what does that tell us about what's really happening when you're sitting in that chair? It tells us something shocking. Right now, as you sit there, the ground beneath you is accelerating upward, not metaphorically, actually. The electromagnetic forces in the Earth's surface are pushing up against you at 9.8 meters per second squared. You're not being pulled down, you're being pushed up, but pushed up through what? Through curved space-time. Think of it like this. Imagine you're driving on a perfectly straight highway. Cruise control set, steering wheel locked straight ahead. You're not turning, you're not accelerating, you're going straight. But now imagine the road itself starts to curve. The road bends left, bends right, goes over hills and through valleys. From your perspective in the car, you feel forces. You feel pushed to the right when the road curves left. You feel thrown forward when you go over a hill. You feel pressed back into your seat when you go up a steep incline. But you haven't changed what you're doing. You're still going straight. The road is doing the curving. That's exactly what's happening with gravity. Mass tells space-time how to curve. Curved space-time tells matter how to move. The Earth isn't pulling on you. The Earth is sitting in space-time, and space-time curves around it. You follow the curvature. But let's make this concrete. The Earth has a mass of about 6 trillion kilograms. That's a lot of mass. And all that mass warps space-time around it like a bowling ball warps a trampoline. The closer you get to the Earth, the more curved space-time becomes. Now here's something that will mess with your head. Time itself runs slower in curved space-time. If you could somehow place an atomic clock at sea level and another identical clock on top of Mount Everest, the clock at sea level would run measurably slower, not because there's something wrong with the clock, because time itself is affected by the curvature of space-time. We're talking about tiny differences. Over the course of a year, the difference would be about 30 nanoseconds. But it's real, it's measurable, and it proves that gravity isn't just affecting space, it's affecting time. This isn't science fiction. This is engineering reality. Every GPS satellite orbiting Earth has to account for this time dilation. The satellites are farther from Earth's gravitational field, so their clocks run about 38 microseconds per day, faster than clocks on the surface. If we didn't correct for this, your GPS would be off by miles within a single day. So when you use your phone to navigate, you're relying on Einstein's understanding of curved space-time. Every time you get turn-by-turn directions, you're using the fact that gravity warps both space and time. When you drop that pencil, it's not being pulled downward. It's following the straightest possible path through curved space-time. What we call falling is just following the geometry. Here's an experiment you can do right now. Take that pencil and hold it out in front of you. Now let it go. Watch it fall. Really watch it. What you're seeing is an object following a geodesic through curved space-time. A geodesic is the shortest path between 2 points in curved space. If space-time were flat, like a perfectly level table, the pencil would just sit there, no motion. But space-time isn't flat around the Earth. It's curved. So the shortest path through that curved space-time looks like accelerated motion from your perspective. This is why Einstein's theory is called general relativity. It generalizes the idea of relativity to include gravity. In Einstein's universe, there's no such thing as a gravitational force. There are only objects following the geometry of space-time. But here's what's really mind-bending. You can't feel this geometric motion. When you're in free fall, when you're following a geodesic through space-time, you feel nothing. No acceleration, no force. It's only when something interferes with that natural motion that you feel forces. Right now, sitting in your chair, you're not in free fall. The electromagnetic forces in the chair are constantly accelerating you upward, preventing you from following your natural geodesic through curved space-time. That's why you feel weight. That's why you feel pressed into the chair. You're being accelerated away from your natural path. Now you're probably asking, why does mass curve space-time? And here's where I have to be honest with you. At some point, you hit bedrock. Einstein's equations tell us precisely how mass curves space-time. They tell us the relationship between matter and geometry. They make predictions that match reality to incredible precision. We've tested them with atomic clocks, GPS satellites, gravitational wave detectors. The math works perfectly. But why does it work? Why does mass warp geometry? We don't know. The universe doesn't owe you an explanation that makes you comfortable. We can describe it, we can measure it, we can predict it, we can use it to navigate spacecraft and detect black holes. But the deepest why question hits a wall. Mass curves space-time because that's what mass does. That's the law. And here's something that should make you pause. This description, this geometric picture of gravity. It only works for large objects. For atoms, for particles, for the quantum world, we need different rules. Gravity stops making sense at small scales. But before we get to that problem, let me tell you about something you can actually feel, something that proves space-time is curved right here, right now in your own body. Stand up and stretch your arms above your head. Now think about what's happening. The atoms in your head are slightly farther from the center of the Earth than the atoms in your feet. That means they're in a slightly different region of curved space-time. The curvature is slightly less intense at head level than at foot level. This difference is tiny. We're talking about a distance of maybe 6 feet in a gravitational field that extends thousands of miles. But that tiny difference creates what we call tidal effects. Your feet want to follow a slightly different geodesic through space-time than your head does. The electromagnetic forces holding your body together resist this differential motion. That resistance creates stress, actual physical stress in the molecular bonds of your body. You can't feel it because the tidal effects of Earth's gravity are incredibly weak at human scales. But it's there. Now imagine you are falling into a black hole. The tidal effects become extreme. Your feet, being closer to the black hole, would want to follow a much more curved path through space-time than your head. The differential would be enormous. The electromagnetic forces holding your body together wouldn't be strong enough to resist. You'd be stretched apart. This is what physicists call spaghettification, and it's a direct consequence of the geometric nature of gravity. We have quantum mechanics for the very small. We have general relativity for the very large. But we don't have a theory that unifies them. We don't know what gravity looks like when a single atom falls. The theory that explains your pencil falling can't explain an electron falling. So here's the uncomfortable truth. Our best theory of gravity admits its own incompleteness. It works magnificently for planets and stars and galaxies. It predicted gravitational waves 50 years before we detected them. It tells us black holes exist, how they behave, what happens to space and time near them. Understanding isn't comfort, it's power. But it can't tell us what happens at the center of a black hole. It can't tell us what happened in the first fraction of a second after the Big Bang. It breaks down. The math gives us infinities, and infinities are nature's way of telling us we don't understand what's really going on. Does that make the theory wrong? No, it makes it incomplete. Every theory has a domain of validity. Within that domain, general relativity is the most precisely tested theory in all of physics. Outside that domain, we need something else. So what should you take away from this? How should this change how you think about falling, about weight, about the ground beneath your feet? First, stop thinking of gravity as a force. Forces push and pull. Gravity doesn't push or pull. Gravity is geometry. When you feel weight, you're feeling electromagnetic forces preventing you from following your natural path through curved space-time. Second, free fall is the natural state. When you jump, when you're in an airplane experiencing turbulence, when you're on a roller coaster going over a hill, those brief moments of weightlessness, that's when you're free. That's when nothing is acting on you. The rest of the time you're being accelerated by electromagnetic forces. Third, learn to think operationally. When someone says gravity pulls you down, ask them what that means. What's the mechanism? How does it work? What predictions does it make? Don't accept labels disguised as explanations. Fourth, direction is relative. Up and down, left and right, forward and backward. These are human inventions. They're useful for navigating your daily life, but they're not fundamental features of reality. In space, there is no up, there is no down, there are only relationships between objects in curved space-time. But here's the thing that should really change how you see the world. Every step you take, you're fighting geometry. Every time you stand up, you're using electromagnetic forces to accelerate yourself away from your natural path. Walking is a constant battle against the curvature of space-time. When you lie down in bed at night, you're not resting from the day's work against gravity. You're resting from the day's work against geometry. You've been fighting the shape of the universe all day. And when you dream, when your brain processes the day's experiences, it's processing a day of curved motion through curved space. Your inner ear, your sense of balance, your proprioception, they're all geometric sensors. They're measuring your relationship to space-time curvature. Motion sickness? That's your brain getting confused about geometry. Vertigo? Same thing. The feeling you get in a fast elevator or on a steep roller coaster? That's your body detecting changes in space-time curvature. You are a walking, thinking sensor for the geometry of the universe. And here's something that should change how you think about movement itself. When you walk across the room, you're not just moving through space. You're moving through space-time. Every step you take is a step through 4 dimensions, 3 of space and 1 of time. Your brain processes this 4-dimensional motion and translates it into the sensation of walking across a room. But what's really happening is that you're tracing out a path through curved space-time geometry. When you run, you're tracing a different path through space-time than when you walk. When you jump, you're following a parabolic geodesic through curved space-time. When you sit still, you're moving through the time dimension of space-time while staying roughly fixed in the spatial dimensions. Even when you think you're sitting perfectly still, you're actually moving through space-time at incredible speed. You're moving through the time dimension at 1 second per second. And because you're on Earth, which is spinning, you're also moving through space at about 1,000 miles per hour. And because Earth is orbiting the Sun, you're moving through space at about 67,000 miles per hour. And because the solar system is moving through the galaxy, you're moving through space at about 500,000 miles per hour. Motion is everywhere. Stillness is an illusion. And all of this motion is motion through the curved geometry of space-time. Let me tell you about the International Space Station. Right now, as we speak, there are people floating 250 miles above your head. They're in constant free fall. They're falling toward Earth at exactly the same rate that they're moving sideways. So they keep missing. But here's what's beautiful. They're the ones who are free. They're the ones following their natural paths through space-time. They're the ones experiencing what it means to exist in Einstein's universe without interference. You sitting here on the ground, you're the one being acted upon by forces. You're the one being constantly accelerated away from your natural path. The astronauts are free. You are captive to electromagnetic forces. Think about this for a moment. The people floating in space, the people we think of as being in an extreme environment, they're actually in the most natural state possible. They're experiencing pure motion through space-time without interference. They're feeling what Einstein's universe actually feels like. We, down here on Earth's surface, we're the ones in the artificial environment. We're constantly fighting against our natural motion through space-time. Every building, every chair, every surface is a machine designed to accelerate us away from our natural geodesic paths. When you sleep in your bed, the bed is accelerating you upward all night long. When you stand on the floor is accelerating you upward. When you lean against the wall is accelerating you horizontally, away from your natural path through space-time. Civilization is essentially a collection of machines for fighting geometry. Architecture is applied anti-gravity, not in the sense that we're overcoming some force, but in the sense that we're constantly deflecting matter away from its natural geometric paths through curved space-time. Does this change your daily life? Not really. You'll still fall if you trip. Dropped objects will still break. Your coffee will still spill if you're not careful. But now you know what's really happening. You're not being pulled down by some mysterious action at a distance force. You're being pushed away from your natural path through curved space-time by the electromagnetic forces in the ground beneath your feet. And here's the most profound part. This geometric picture of gravity doesn't just explain falling objects. It explains the expansion of the universe. It explains black holes. It explains gravitational waves. It explains why time runs slower in strong gravitational fields. It explains why GPS satellites need their clocks adjusted. But let me give you an example that's even closer to home. Right now, the light coming from your ceiling lamp to your eyes is climbing out of Earth's gravitational field. Not much, maybe 8 or 10 feet, but it's still climbing upward through curved space-time. When light climbs out of a gravitational field, it loses energy. It gets redshifted. The light hitting your eyes right now is very slightly redder, very slightly lower in energy than the light that left the bulb. The difference is fantastically small. You could never detect it without incredibly sensitive instruments, but it's real. This means that the simple act of turning on a light and looking up involves the geometry of space-time. The photons leaving the bulb are following geodesics through curved space-time, just like falling objects. Because they're massless and moving at the speed of light, they follow null geodesics paths through space-time that have zero length in the space-time metric. Even more bizarre, if you could somehow shine a flashlight beam horizontally, that beam would bend downward as it travels. Not because something is pulling on the light, but because the light is following the straightest possible path through curved space-time. What looks like bending from our perspective is actually straight motion through curved geometry. All of this, all of modern cosmology, all of our understanding of space and time comes from taking seriously the idea that falling doesn't feel like falling. Einstein started with that simple observation. In free fall, you don't feel your own weight. From that one insight, he rebuilt our understanding of space, time, matter, and energy. He followed the logic wherever it led, even when it led somewhere uncomfortable. So the next time you drop something, the next time you feel your weight pressing down into your chair, remember you're not falling toward the earth. You're being accelerated away from your natural path through curved space-time. The universe is stranger than your brain wants it to be, but it's also more elegant, more unified, more geometrically beautiful than the patchwork of forces your intuition suggests. And here's the deepest truth. Your intuition about falling, about weight, about up and down, these intuitions evolved to help you survive on the surface of one particular planet. They are local adaptations to local geometry. They work perfectly for throwing spears and catching fruit and avoiding falling off cliffs. But they're not universal truths about reality. If you had evolved in deep space, far from any massive objects, you wouldn't have developed these intuitions at all. The concepts of up and down would be as foreign to you as the concept of purple is to someone born blind. If you had evolved on a planet with stronger gravity, your intuitions about falling would be different. If you had evolved on a planet with weaker gravity, they'd be different again. What you think of as normal gravity, what feels right to you, is just one particular strength of space-time curvature. There's nothing privileged about Earth's gravity. There's nothing special about 9.8 meters per second squared. It's just the local value of space-time curvature at the surface of this one particular ball of rock, orbiting this one particular star. But by understanding that your intuitions are local, by recognizing that falling doesn't feel like falling because falling is the natural state, you can begin to see beyond the boundaries of your evolved perceptions. You can begin to understand reality as it actually is, not as your brain evolved to perceive it. Understanding isn't comfort, it's power. And now you understand why falling feels wrong, because it is wrong. You're not falling, you're being held back from falling, and that makes all the difference.